And apparently we are recording sound check.
Yeah, we can hear you.
Okay, and I can hear you too. Okay, so attendance. Dalton is here, Eric is here. Oh, wait a minute, is Dalton here? Dalton is not here, I was confusing. Okay. All right, back to that. So Eric is here, Caleb is here, Brandon is here. Was Kevin able to make it today? Okay. He must be feeling very poorly. Michael. I don't see Michael. I saw Connor. Did I see Connor? Connor. Yeah,
here.
sure I did. Yep. In the game that is Zoom in Hollywood Squares, you're right in my center, right? So, okay, RJ, I don't see yet. I see Davison, I see Chris, I see Sydney, I see Blake and Joseph. Is Joseph on camera with in a room with anybody else? Anybody?
He and Dalton are at the CubeSat Developers Workshop in California this week.
Okay, got it. Thank you.
Yep.
And that turns them green with envy. I wish I was in California. So Blake S is here. Dan, I have not seen. James is here. Amanda, I do not see. Alejandro, I do not see. That's too bad. Nicholas is here, Noah is here. Okay, so these are the people that I have. Let's see, no, I confused those two people again. All right, so I have Kevin and Michael as absent. And I have RJ as absent. And then three more. I have Dan and Amanda and Alejandro. So has Amanda arrived? No. Okay, so the attendance is saved. All right, now, yeah, I'm glad I turned on the camera for you to see that and for me to cough in your ears. Sorry. Okay, so and as soon as I hit save, that's the signal for folks to come to class. Okay, Alejandro, I have you marked present. Okay, all right, so apparently in project 2, we discussed files a little bit. And if I recall, that had to do with statting information about the metadata of a file, right? Okay, all right. So let me start out class by projecting. And by projecting, I mean not in the psychological sense. Okay. So my first question to you is, tell me, what do you think it is that a file system is? You've heard the word, but what is it? What is a file system? Discussion time, everybody.
How an operating system handles saving and retrieving files.
How? that while it's a good answer, Brandon, I'm asking a what question. So what is a file system? And you can look at the next question. What is the role? What is the purpose of a file system?
A file system
File system.
should give like a logical way of finding all the information you need on the computer. You
Yeah.
could find things that are in like your desktop, you would follow like that map. It's almost like a tree towards where you want to find information.
File system's like more of a process for finding files rather than like an actual thing.
Okay, so so first let me say, Nicholas, that was excellent. As you can see that I'm adding what you said. So does this capture what you said?
Yes.
Yeah. So so Nicholas, you're identifying that what a file system is seems to be a data structure. And Noah, it sounds like what you were saying is that a file system is an algorithm.
Yeah.
Okay, okay. So at this far in, having come this far in your education in computer science, you know that data structures and algorithms always seem to come together. You don't have a data structure without an algorithm and with which to navigate it. And you don't have an algorithm that doesn't operate on data. So, okay. So Noah has a good answer. Nicholas has a great answer. What else? What is a file system?
For key attributes, I know each directory has a reference to itself and its parent.
Okay, so it is a way of maintaining key attributes, and we'll get to that later on. You see the word, I have the word attributes written on here already. So good, Connor, thank you. What else? Okay, who's taken the database course? Raise your, whatever it is you have.
The data structures course.
The database course.
Oh,
Okay, let's see. Let me mark, take care of RJ here. I've got to find, there it is, just the slimmest. Okay. And of course, I have to move. Okay, RJ, RJ, I've got you marked present.
Thank you.
Okay. And okay, so forgive me, what was the last thing that a student said?
I was saying that each directory has a reference to itself and its parent.
Okay, so part of the role of an operating system is organizing the directories and into a data structure. The data structure that we've heard that it has so far, and indeed is a truism, is that the data structure is hierarchical in nature. So you have an idea of a node, which is a directory. Leaf nodes may be directories or files, but internal nodes are directories. Okay, and it seems to be a kind of doubly linked list with reference to directories. As Connor just said, a parent directory has a link certainly to its child directories. That's a single link in one direction. And child directories have a link back up to the parent, making it a doubly linked arrangement. Good. Thank you, Connor. What else? So let's think about, I started to mention the database course. Now, does someone who's taken the database class, can you explain to me this in database? And let's see if we can apply any of these to file systems. Anybody remember what ACID stands for in database?
It stands for autonomicity, consistency, isolation, and durability.
Yeah, thank you, Nicholas. The way the sounds that you began with, I was thinking, uh-oh, we're going in the wrong direction. But in that first word, you then did a curveball to the right direction. So good. So atomic, consistent, consistent. Anybody know, is it ANT or ENT? Let's call it ANT. Anybody know offhand? Any good spellers here? I'm a mediocre speller. Okay, isolated. And what was the D?
Durable. Durable.
Okay. All right. So is it, do any of these apply, do you think, to operating systems? I mean, sorry, to file systems?
It's got to be durable. It always has to work, and it always does work.
Okay, for file systems, for sure, definitely. Durable means that once you write something, it's written. Okay, so we don't, a properly functioning computer, you don't turn it on one day and find the things that you wrote the day before are gone. That's not supposed to happen, although I'm sure it can happen if there's a hardware failure, for example, or your computer is infected by malware that encrypted or deleted everything. But in normal functioning, durability is certainly one of the aspects of a file system. A file system data structure and algorithm should be designed in such a way, and hopefully we'll see an example of this, designed in such a way as to increase the durability. Okay. What's another one of these that a file system would also want to implement?
All the files have to be atomic. That's why when you like save a file and it already exists, it'll like tell you, and you can like rename it if you want to duplicate it.
So atomic means that once a write starts, it runs to completion.
Ah, you're right. Sorry. You're right.
Okay. So no, I think you've got some merit there too, Nicholas. So a file system, applications should be able to assume that once they've written something, it becomes durable. So atomic, you can think of writes to the file system as being atomic, although it's not clear at this moment when that happens. For example, with an atomic database operation, namely a transaction, when the transaction is complete, everything has been written. Now, an application that writes to a file assumes that it will get written to the disk. It is entirely possible that the operating system could crash before buffered data reaches the durable stage. So with the exception of, let's say, OS crashes or a machine turning off, we can think of a write to a file system as being atomic. Okay, so let's put a check mark next to that. All right, what about the other two?
Would isolated mean that a different like database or algorithm can't access it?
So someone from the database course, can you help us with the definition, the database definition of isolated?
Well, isolated means when like you have multiple transactions happening at the same time, it treats it as if they were like executed sequentially, so like one after another, so that you don't overwrite something important.
Mm-hmm.
So you can't treat it as like multiple threads or something.
Well, we can write to the file system. We can even write to the same file in multiple threads. So how about we sort of leave this one with a maybe. Okay, but what about consistent? Do you think that it would be a good idea to have an inconsistent file system? Doesn't sound good, does it? Okay, so I create a file in a directory, and I look in the directory, and maybe it's there, maybe it's not. It's Schrodinger's file. I don't know. So yeah, we definitely should have some consistency in the file system. So I've mentioned before that database internals, the way that a database management system is written and the way it operates, borrows a great deal from operating systems, and operating systems borrows a great deal from database. So here's another example. Pretty much the ideas behind ACID from a database translate pretty well, not completely, but pretty well to file systems. Okay, so key attributes, purposes, and roles of a file system, definitely to organize files and directories, to create a consistent data structure so that the hierarchy of files can be traversed, that there are no errors, there are no like dangling pointers, so to speak, in the management of a file. And also has to give some way of making the rights durable. Now, what else? Okay, so now let's drill down a little bit. What information do you think we should keep about files? We may have discussed this in class. So what information do you think we should have about files?
A pointer to where it exists and what is actually in it. So maybe it's like
Where
a pointer to the first element of an array of something.
Where is the data? Yeah, if you can't find the data in a file, then the file system has failed in its role. Absolutely.
We should also keep track of how big it is.
Okay, good. That's good. Good. We should definitely know that. Why should we know that?
So when we write our next set of data, like we always know that we have enough room within our data structure.
If we want to write at the end of the file, we need to know where the end of the file is. If we want to overwrite something in the middle, then the size is not so important. But most writes are appends. They go at the end of the file. Okay, good. Also, it's just fun to know, right? You do an ls minus l, you want to know how big it is. Okay. What else? Well, think about what it is that you have wanted to know about a file in the past.
Sometimes you need it, you need to get like the .c file, or if it's Python .py, if the file has a certain type, or .stl for 3D printing.
Okay, so name? Nicholas, should we, I mean,
Yeah, I
is
guess
that
it
what
could
you're
be
getting
part
after?
of it, part of the name, yeah.
Okay, all right. We're gonna come back to name. Keep going.
Date when it was last edited or something.
Okay, date. And what kind of dates? Last edit. So when has the file changed? What else? Any other dates?
Creation date.
First made.
Creation, good. There's actually a third date that's kept track of on many file systems, when was the file last modified and when was it created are definitely two that are kept by all file systems. Well, most file systems. Okay, what else?
You also might want to know like the type of data contained in the file, like if it's text, if it's like video information, if it's like an image.
Do you think the operating system needs to know that?
That is true. It probably doesn't. That'd be something more for the like whatever's
For the
application.
applications.
Yeah.
Right, right. So type, no. Okay. In fact, let's digress for a moment. Some operating systems depend upon the file's name to determine the file's type, and that's really, really stupid. Linux and Unix derivatives pay no attention to a file's name with regard to its type. Okay, so instead, how do you think applications figure out if a file has the right type? Instead of looking at its name, which applications might do.
Isn't there
But-
usually like some kind of identification, like in the very first few bits of the actual file that say what it is? Kind of like on Windows executable, it's like a PE or something it says in there.
Brandon's got it. Yeah. So applications should not depend. Certainly the OS does not depend on a file's name. Instead, applications will sort of just taste. They'll take a taste out of the file. They'll sniff the file. You know, they take a lesson from dogs, I guess. But they'll take the file, they'll give it a sniff, and they say, yeah, this smells like a JPEG file. This smells like a shell script. So they literally, applications should literally open the file and look at, let's say, the first 512 bytes and see if what is supposed to be there is there. Okay, so good answer, Brandon. What else? There's a whole bunch of things that nobody's mentioned. You got lots of opportunity for right answers.
The location of the file.
Let's see. So are you referring to the data? Because I have that written already.
Oh yeah.
Already.
Yeah.
See, I just that was a tiny slip of my upbringing. Did you hear it, everybody? I corrected it. I have that written already. So, hey, I got that written already, all right?
Yes.
I don't usually sound like that, do I? But so already. Forget about it. All right. So what about security? What about ownership? What about access rights?
So file permissions, like user or group permissions.
Yep. So the file permissions. And Brandon also,
Drivers being only accessible to the admins.
yes, Noah, right? Access rights. So file permissions, I'll put in parentheses access.
Also, like
And
group permissions, like for Unix systems.
okay, so different types of permissions. Maybe there's different roles that would have access to a file as a part to other roles. And that's in fact in a Unix style environment that is called groups.
Would be a read writable executable type that you see in Unix when you use ls count as like file permissions, or would that be like it's a different thing as well?
Well, those are definitely the file permissions. Now, it turns out that some file systems have more complex and nuanced file permissions than others. So when we see read, write, execute, read, write, execute, read, write, execute, those are the basic Unix style permissions. And that refers to what can the owner do, what can the group do, and what can everyone else do. And you've got read, write, execute. So read, obviously, can you read this file? W for write, can you write to this file? And X, can you execute this file? Now, interestingly, directories, which are files, by the way, they also have X. Does that make any sense? Can you execute a directory?
Oh yeah, if directories are files, then I'd say you can, because there are such things as like .exe files.
Right, right. But a directory is just an organizing component in the data structure of the file system. So what would, if I tried to execute a directory, what actually would execute?
I feel like the only thing you can do is just go there. But maybe I'm wrong. Oh, they do have executable?
Go there. Okay, so let's take that. Would that be read permission?
That would be read permission, because you would be able to see like whether it's a directory to another directory, if there are files there.
Okay.
So it'd be like a code, I
Yep.
guess.
Well, Nicholas is really close to the right answer. Why directories have X values? It turns out that it's, can you search the directory? So if you were to say /A/B/C, what you're trying to do is, let's say this is an executable. Let's say that's a program. Okay, so if you did not have read permission on B, you might not be able to do an ls in B. You might not be able to change directory to B. But if you do have the X, which otherwise would stand for execute, in terms of a directory, it means you can traverse through it without stopping there. So even if I didn't have full permissions on B, if the X bit is set, that means I can't do an ls and find C, but if I know it's there, I can get at it. Okay, so that's what, so the answer here is traversal. So the X bit is kind of repurposed for directories. Okay. So this is a lot of information that file systems we agree should keep. Now let me ask you this question here. Should well, let me modify a little bit. Should directories include file names? Or should, I'm sorry, let's ask the opposite question. So there's a nugget full of metadata about a file. And in that nugget, which let's give it a name, we've heard the name before. That's the inode, which if you look up historical interviews by the creators of Unix, they will say, or I've heard them say, they don't remember why they named an inode, but it seems clear to me, it's clear to me at least, that it just means information. It doesn't mean that it was an early Apple product. You know, Samsung had nodes and Apple had inodes. But no, it's just information nodes. So the inode that we saw in project 2 contains a great deal of the metadata about a file, but it doesn't include its name. Why do you think that is? So what about all of these, including this? Well, yeah, including that. All of those really do need to be unique, right? I mean, for example, if we had multiple inodes for a file, the inode includes where is the data. Isn't it possible that we could become inconsistent if we didn't keep all the same inodes referring to this, all of the inodes referring to the same file? Unless we kept them consistent, we would have an inconsistent file system, right? So it makes sense to have a lot of the information about a file to be kept in a unique location. So I guess the question I'm asking you is the name of a file unique? Is it deserving of uniqueness?
I guess only if it's in the same directory, because you can have like file x.c, but you could have the same name in 2 different directories, just not in the same one.
Okay. Give me a second. Let me click a button. All right. So what are you seeing now? Linux? Okay. So so I'm going to make a directory. I'm in the directory, ls-l. There's nothing in the directory. That's not completely true. There is something in the directory. You need to do the A option to see any file that begins with the letter period. Okay, and as I believe Connor discussed, you do see a link to the current directory, which is called dot. Every directory has a name for itself, just like your baloney. Boy, I'm full of terrible references today. Does anybody want to sing the song? This is a liberal arts college after all. No? Okay, you can come off speaker now. We can sing it together. my. Okay,
What is going
never
on?
mind. What's that?
What are you even referencing in the first place?
My baloney has a first name. It's Oscar. My baloney has a last name, Meyer. No? Okay. You're all too young. All right. So Oscar Mayer Baloney has a unique name. I was making an allusion to it here. So every directory's name for itself is dot. Every directory's parent's name is dot dot. Which begs the question, what do you do with the root directory? We'll find out later. Okay, so once again, we're here in this directory and we're on the subject of file names.
Wait. If every directory's parent name starts with dot dot, why don't we need to specify the dot dot when we cd to something in Linux?
Oh, we can, by the way. So, ow, that hurt. Thank you, Linux. All right. So if I were to do a print working directory, so foo is a child directory of TMP. TMP is the parent of foo. You can actually use, and often do use, dot dot. Right? So cd foo dot dot foo, and where are we? In foo. Okay, Noah? Right. So in this case, what you're seeing here is /temp is truly the name of the parent of foo, but in an absolute namespace. In the namespace of the current working directory, no matter where it is, dot dot is your parent. Okay. Now we're all familiar with using dots. Oh, it did it again. Dot slash, right? We would do dot slash a dot out. And that's because we are referring to the current directory without needing to know its name. This is not going to work because there is no a dot out. Okay. So I'm going to create a file.
That's because we didn't compile it yet, right?
Right. We didn't compile it. We have no source code. We have, there's no executable here. So I created a file. There is the file, ls-l bar. It was created at April 25th at 2:13. It has the name BAR. It's owned by a user named Parallels. Who am I? I'm Parallels. And it's owned by the group Parallels as well. So owner and group. Here are our 9 permission bits. There's also an extra one there. So read, write, no execute, read, write, no execute, read, no write, no execute. This says I, as the owner, can read and write to the file. Anyone in my group can read and write to the file. And everyone else can only read the file. So RWX, being a group of 3, lends itself to numerically as octal. So if I were to change the mode of bar to 666, it is not the sign of the devil. It is just adding write permission to everyone. ls-l bar. And now you see the addition of the W here. So 6 means 4 and 2 add together make 6, right? Anybody have any questions about that? Now, Chmod, if you want to look up Chmod, you'll see that it does actually support other syntaxes. So if you, for example, use the plus sign or letters, you don't have to remember octal. Okay, so it does have an alternate syntax that was added later in the life of Unix. But now let's get back to this idea of name. I'm going to link bar to bar 2. ls. Now I've got two files. ls minus l. Look at that. They both have the same permissions. They both have the same date, same owners. Does anybody see a difference here besides the file name? A difference between that and these?
Or two.
Well, the names are different, sure. And that goes back to, I believe, what Brandon was saying. Is that right? Or no, maybe it was, I'm sorry, I don't remember who was saying that within the same directory, you can't have two files of the same name, but you can have files and any number of files of the same name if they're in different directories. Connor, was that you?
I believe it was Nick.
Nick, okay. Brandon? Nick, okay. All right, so anybody see the difference? Okay, here I see a 1. And here I see a 2. Any guess as to what that means?
But yeah, but the two bottom ones at the bottom both have 2, but they're labeled as bar and bar 2,
Correct.
respectively.
Yes, true. What can you make of that? Hang on. I'm going to make a third one. ln bar to bar 3, ls minus l.
Oh, okay, I get it. It just depends on the number that you specify in bar, and that specifies how many are created.
No. Let's try this. Bar to door jam. Okay, so we were on the subject of file names. So the name of a file is not part of the metadata that is unique to the file. The name of a file is a way of identifying which file you're talking about, certainly. But here I have an example where I have 4 different names for the same file. Well, you know what? Move door jam to door jam. Let's see if that changed anything. Nope, didn't change anything. So these are all links to the same file. Now, I know something special is going on because this is the link count. This is the number of directories that refer to this file. Let me say that again, but more correctly. The number of times any directory refers to this file. It's not the number of directories. Here I have one directory referring to the same file 4 different ways. Tell you what, let's do this. Echo greater than, hello. that's not what I meant. To double greater thans to bar. And nothing's really changed, except I just updated the time the file was changed. And notice it changed the update time of all the files. Cat bar says hello, and cat bar 3 says hello. They are the same file. And now I'd like to prove to you on a deeper level that they are the same file, ls-li, and that is telling us which inode manages the file. And notice it's exactly the same inode number. So there is proof certain that all 4 of these names refer to the same file. Any questions? Oh, well. All right. So the reason I'm doing this, by the way, on Linux and not on my Mac is Apple. So Linux is behaving the way it's supposed to, and sometimes Apple just doesn't do things the way everyone else in the universe does. Okay, so we were talking about metadata for the file. We know that the metadata that is unique to a file goes in the file's inode, and that does not include the file's name. If I were to remove bar 2, bar still exists. The link, notice the link count has gone down. Okay, but the data is still there. And in fact, the data will stay there until the link count goes from 1 to 0. When the link count goes to 0, it means no one is referring to this file. Therefore, the data in the file can be deleted. Let's do that. So rm bar, what's the link count? 2. Rm bar 3, the link count is now 1. And while we're here, let's look at ls minus lia. So there's a link count for 1 of the remaining link to doorjam. That's the original file. So rm doorjam. Now, does that change anything in the link counts of the directories? No. Now, I told you that the link count is the number of times that a given file appears in a directory, any directory. So why do you think, here's my empty directory. Why is the link count of dot 2? Well, the current directory has a name for itself called dot. So this directory appears in this directory. And what about in the parent directory? Okay, there's the second name. So the reason why directories have a minimum, except on Apple, a minimum of 2 links is because the directory has a name for itself and the parent has a name for it. Okay. All right. So what does a file system look like? Well, I'll go over the first version of the Unix file system. And we have not done this before, correct? Good. So the first Unix file system, which goes back to the 1970s, looks like this. This is all of the entire file system. It's all the blocks that are contained in that file system. The very first block is a special block. That is the super block. So block 0 is the super block.
Wait,
That
is the file
sounds.
system supposed to be on your screen right now?
Thank you, Noah. You got me. Let's go back there. It's coming. There it is. All right. Thank you. So the block 0 of the file system is the super block. And by the very name, it sounds important. What do you think the super block has?
Contains various forms of metadata.
About?
The file system.
Yes, it has metadata about the entire file system. For example, how big is the file system? Okay. All right. Very good. And what comes next?
The Inode block.
Yes, so there's going to be some number of blocks containing inodes. It's just an enormous array. What the hell's an array? Enormous array of inodes. And the original Unix inode, let's see, a block was 512 bytes, and there were 4 inodes per block. Today, so that means 128 bytes per inode. Today, inodes are bigger, but blocks are also bigger. Typically, a block today is 16 512 byte blocks. Okay. All right. So block 0, then block 1 through n were inodes. 4 per physical block. So the length of the inode array determined the maximum number of files and directories that could exist on this file system. So the initial Unix file system was made with a pre-baked limit as to how many files and directories there could be. You could conceivably create one enormous file that would fill the file system, and that meant you couldn't create any more files because all of the data blocks were used, right? So you could fill all of this with one file, or you could fill this with empty files. So many empty files that you couldn't use any of this space because this space was consumed. Okay, modern Unix file systems and Linux file systems have a much relaxed set of constraints. the number of inodes aren't in a modern file system, the number of inodes aren't pre-baked. The inodes, that gives you an idea that the inode array is no longer a single contiguous array in a modern Unix file system, but is instead a data structure that can grow. Okay, and then comes the data blocks. Okay. Now, let's take a look. Let's answer this question here. Where is the data? And for that, we go inside an inode. All right, there is inside an inode an array of, think of them as block pointers. They're not addresses, they're just simply block numbers because the file system altogether is just an array of blocks. So there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are called direct block numbers. So remember also we have the size inside the file system, inside an inode. So if the block size was 512 and thank you, Freda. Okay. So if the block size was 512 and the size of the file was 8, you would expect that only the first direct block would have a value in it. The rest would be zeros. Let's say the block size again was 512 and the file size was 1,000. How many would you expect of the direct pointers to be filled in? Well, 1,000 is less than twice 512. So, okay, so 2 of them. Let's say the size was 1,025. Okay. Just that one byte would cause another single direct block entry to be filled in. So do you get the idea of what the direct blocks are? The direct block numbers. If you go to block number N, you will find the first block of this file. If you go to block number M, you'll find the second block. If you go to block number P, you'll find the third block. But according to this, I can have at most 10 blocks in a file. So I'm asking you, is the size of a file limited to 5,120 bytes?
No.
Of course not. So, okay, computer people love hierarchies. Everywhere we can stick a tree, we stick a tree. So would it be surprising to you that the way that the file data blocks are kept track of using a tree structure? Okay, so, oh, I got it exactly right. So here is the single indirect block. Here is the double, and here is the triple. So let's say this block number was S. If you go to block number S on the file system, you will find a block of data where this is just an array of more block numbers. So here's block number 11 of the file. Here's block number 12 of the file if it's filled in. Each block number was 4 bytes, and this is in a 512 byte block. So this would be 128 more block numbers. So far we've got 10 direct, and then we've got 128 single indirect. Guess what the double indirect is? So let's say this was block number D. If you went to block number D, it would be 128 block numbers of of more block numbers data. So it's a tree structure. So the double indirect means it's the block number of a data of a block that contains 128 block numbers of data. Okay, so let me say that again without reusing the word data too much. A double indirect block contains the block numbers of 128 data blocks. Okay, so this is going to be 128 squared double. And guess what triple is? That would be 128 cubed. So if you add these together, that was the file size limit on the original Unix file system. So it would be 10 plus 128 plus 128 squared plus 128 cubed times 512, because there's 512 bytes in a block, and that would be the maximum file size on the original Unix file system. Okay, and that is how data is located when your application seeks to a particular place in the file. That place in the file is converted into which block within the array of blocks in this file would that block be. And then if it's less than 10, if it's 0 through 9, it's a direct block. If it's 10 through 137, it's a single indirect, et cetera, et cetera. Okay. You'll notice that the blocks consumed by the tree's internal nodes are not counted in the file size. So this double indirect block, which is the root of a layer of tree of height 2, is this particular block is not counted towards the file size. Anybody have questions? Okay, so this architecture is pretty much the way it is today, even on ultra modern Linux file systems. Okay, this is a good idea. Tree structures are good. All right, then I'll see you on Wednesday. Come wearing a smile. And we'll say adieu.
Thank you.
Adios.
Thank you.
Adios.
You have like a question in your operating systems class. Do we go into more detail, like writing the part of the operating system that deals with the hard drive or the how it implements the file system?
There's a cool project in the OS class where I give you 10 or 20 broken file systems. And your project is to write the code that identifies what went wrong in the file system. So yes, you need to go into a lot of detail of a file system in order to diagnose those problems.
And also one more thing, since hard drives, solid state drives, all that stuff isn't technically probably understood by, I guess, the CPU, that stuff essentially needs to have like a driver for it to know how to communicate with that stuff, right?
On several levels, in fact. There's the hardware driver, which is simply responsible for reading and writing. Okay, and then above that is a file system driver that understands the file system. Above that is a buffering system.
What would the buffering system do?
The buffering system is part of the IO subsystem that its function is to speed up operations on the file system. So for example, if you read a single byte from a file, the buffering system will load the entire block and potentially several blocks after that block into RAM so that the next byte you refer to is going to be available faster. So think of the buffering system as very similar in nature to having a cache of file system data in RAM. That's actually an accurate description.
Okay, thank you.
You're welcome. Thanks for asking the questions.